Hey everyone, welcome to this explainer. We are jumping straight into the absolute cutting edge of AI memory today, and that is GraphRAG multi-hop retrieval. Now, if you've been following the evolution of retrieval augmented generation, you already know the biggest hurdle we face, finding the exact right context so an AI can answer really complex questions. To show you exactly how this works under the hood, we're going to use the full stack GraphRAG hierarchical chat project as our blueprint. It's a really fantastic production-ready application that nails this approach. To set the stage here, I want you to picture yourself as a detective. You're tasked with answering a very specific question. How is Dr. Elena Reyes connected to Marcus Chen? The problem is the clues aren't just sitting together in one neatly organized file. They're scattered all across this giant, tangled web of evidence. Maybe document A mentions Dr. Reyes working on a specific project, and then way over in document B, it mentions Marcus Chen funding that exact project. Standard search totally struggles here. We need a system that can actually follow the trail. To see how we connect those dots, here is our roadmap for today. We'll start with 1, beyond simple vector search. 2, multi-hop agentic retrieval. 3, inside the LangGraph loop. 4, the underlying data model. And 5, accuracy versus latency trade-offs. Let's get right into it. Section 1, beyond simple vector search. Let's see why those traditional methods kind of fall flat for our detective scenario. Look at the contrast here. It's pretty stark. Standard vector search is heavily reliant on semantic similarity. That's great if the answer lives neatly in a single paragraph. But if the facts are spread out across multiple different passages, a simple vector search is just going to completely miss them, mostly because those fragmented pieces might not directly match your initial query. GraphFusion, though, it actively hunts them down. It recovers those facts using what's called n-hop traversal, literally jumping from node to explicitly connect those relationships. So here is the absolute crucial takeaway. We aren't just trying to find a paragraph that holds the answer. We are literally assembling answers from thin air. We're combining these tiny fragments of relationships into a single, coherent truth. Even though no single passage states the answer outright, by analyzing the whole knowledge graph, the AI deduces the connections to give you a highly accurate synthesized response. It's like putting together a massive puzzle without seeing the box. Moving on to section 2, multi-hop agentic retrieval. Let's see how this system actually builds out that connective tissue using an autonomous agent. Our chief detective for this blueprint is the LangGraph multi-hop agent. Basically, this system loops through 3 distinct phases: vector retrieval, entity linking, and graph traversal. But the real magic? It's right there in the reseeding. Think about it. When the agent finds a new clue, like a newly discovered graph neighbor, it takes that fresh information and uses it to seed the very next hop. It's constantly grabbing a clue, linking it to a suspect, and branching out to see who else they might know. Now, this incredibly powerful agent runs on a seriously robust modern stack. On the back end, you've got FastAPI handling the heavy lifting, using server-sent events, or SSE, to stream answers token by token. That means the user isn't just sitting there staring at a loading spinner. Up front, there's a Next.js interface with a Cytoscape chat UI that beautifully renders the knowledge graph visually. Under the hood, LangGraph runs the logic, Qdrant stores the vectors for lightning-fast similarity searches, and Neo4j acts as the ultimate source of truth for the actual graph data. Cap it off with an OpenAI-compatible LLM, and the best part? This entire blueprint can run entirely locally using tools like Llama or vLLM. No expensive API keys required, so your budget is definitely safe. Okay, section 3, inside the LangGraph loop. Now that we know who the players are, let's pull back the curtain and look directly at the procedural loop itself. This brilliantly illustrates the exact journey a query takes. Step 1, the agent retrieves those initial vector matches from Qdrant based on whatever prompt you gave it. Step 2, it takes those text chunks and links them to explicit entities sitting over in Neo4j. Step 3, once it has those entities, it traverses the graph, traveling along typed edges to find connected nodes, the neighbors. And finally, step 4, it checks its configuration. If more hops are allowed, it grabs those newly discovered neighbors, reseeds its search criteria, and runs the whole thing again. It just keeps digging until it either hits a hard limit or finds the complete answer. But for this whole sophisticated loop to run smoothly, the data has to be impeccably organized. Which brings us to section 4, the underlying data model. So Neo4j structures our data hierarchically. Right at the top, you have the document node. That's your root source file. Directly beneath that is the parent chunk, which is a nice, large text block. Underneath that is the child chunk, a much smaller text block. And then finally, we have the entity nodes. These are your actual extracted concepts, people or companies, linked right to the chunks through explicit typed edges. This structure is exactly what lets us separate the search process from the generation process. Check out this number right here, 200. That is the default token limit for a child chunk in this system. You might be wondering, why make it so small? Well, child chunks are designed specifically for highly precise embedding and vector retrieval in Qdrant. A smaller chunk means the semantic meaning is super tightly focused. So when you do a vector search against a 200-token chunk, you are getting incredibly accurate pinpoint matches. But when it comes time to actually generate the answer, we jump up to this number, 1,000. The system automatically expands its scope from that tiny 200-token child chunk all the way up to its corresponding 1,000-token parent chunk. We call this small-to-big indexing. You search on the small child to find the exact needle in the haystack, but then you pass the giant parent to the LLM. That is what gives the AI the rich, surrounding context it desperately needs to understand the relationships and output a really high-quality answer. Because we rely on this explicit hierarchy, we get something amazing: provenance mapping. Every single entity and relationship maintains a strict, unbreakable link right back to the exact chunk ID it originated from. In Neo4j, that looks like an entity node connected via a mentioned-in relationship directly to a child chunk. Because the data model strictly guarantees this provenance, the front-end UI can stream exact token-by-token citations and render a beautiful, interactive graph inspector. The user sees exactly where the AI pulled its facts from, so no hallucinations, just hard evidence. Section 5. Accuracy versus latency trade-offs. To wrap things up today, we have to talk about constraints. Because let's face it, acting like a thorough detective takes time and serious computing resources. Looking at these default settings, it's pretty clear we have to put guardrails on the system. Max hops and max iterations are both capped at 2. Top K, which is your limit for vector results per hop, is set to 5. These constraints are absolutely necessary. Every single hop the agent capes adds more Cypher database round trips to Neo4j and triggers another secondary vector query to Qdrant. If you just let the agent hop infinitely, sure, it might eventually stumble onto the perfect answer, but it'd be like falling down a Wikipedia rabbit hole at 3 a.m. Your user would just be staring at a loading screen forever. It's the exact same deal with the small to big context expansion we just talked about. Sure, blowing up to larger parent chunks restores all that juicy context and drastically improves the answer quality, but the downside? It seriously bloats your prompt size. Shoving multiple 1,000-token chunks into your LLM costs way more prompt tokens, and it will noticeably slow down your generation latency, especially if you're running a CPU-first local LLM. It's a constant, tricky tug-of-war between quality and speed. So I want to leave you with this final thought. As you look at rolling out hierarchical chunking and multi-hop retrieval in your own projects, how are you going to configure these settings? Where exactly is your perfect balance between the relentless hunt for graph-driven truth and the undeniable need for a lightning-fast pipeline? Thanks for hanging out with us for this explainer, and we really hope this gives you a much clearer picture of how GraphRAG multi-hop retrieval is working under the hood.